Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Evaluating the interaction between terrestrial microanimals and simulated extraterrestrial environments establishes the core objective of this scientific analysis.
It is a critical examination. Specifically, the analysis focuses on tardigrade activity. This activity serves as a primary biological health indicator when the organisms are exposed to simulated Martian mineral deposits, which are commonly known as regolith.
The findings under review are formally attributed to an international research team. This team was co-led by Professor of Microbiology Corian Bakermans at Pennsylvania State University, specifically the Altoona campus, alongside co-authors Matteo Vecchi from the Institute of Systematics and Evolution of Animals at the Polish Academy of Sciences, and Gillian Pierce from Aston University.
The resulting empirical study was published in the International Journal of Astrobiology in 2025. It is necessary to contextualize this research within a dual theoretical framework.
Yes, there are two intersecting paradigms here. The first is the utilization of in situ extraterrestrial resources for human exploration. This includes concepts such as utilizing local substrates for agriculture.
And the second paradigm involves the strict regulatory mandates of planetary protection. This dictates the prevention of biological contamination. To analyze this intersection, you must first understand the biological profile of the specific organisms utilized in the assays.
The taxonomic identification specifies two exact organisms: Rhamazodius, cf. Varionordos, and Hypsibius exemplaris.
These are microanimals commonly referred to in the broader discourse as tardigrades, or water bears. Providing a rigorous breakdown of their physiology requires noting that they exist in two primary physiological states.
Active and dormant.
Correct. The mechanisms of dormancy are highly specialized. The dormant state is typically achieved through severe dehydration.
This physiological adaptation allows the organism to survive extreme environmental gradients. When subjected to desiccation, the tardigrade expels the majority of its internal water and synthesizes protectant molecules to stabilize cellular structures.
That stabilization is what categorizes them as extremophiles. You can document specific extreme conditions survivable in this dormant state. Research has established they can endure the vacuum of space, extreme oceanic depths, and near absolute freezing temperatures.
However, you must contrast this dormancy with the active state. When the organism is rehydrated to resume normal metabolic function, it becomes biologically delicate.
It is significantly more vulnerable. Although it should be noted that even in the active state, tardigrades possess the capacity to withstand freezing temperatures and severe fluctuations in food availability.
But they require a microscopic layer of water for gas exchange and locomotion. This requirement is why activity is utilized as the primary methodological biomarker.
Yes, normal locomotion is the metric for assessing the health and survivability of the organism in these astrobiological assays. If it is moving, it is viable.
Having established the biological baseline, it is necessary to examine the environmental substrate. You must formally define regolith.
Regolith is defined as the layer of loose, unconsolidated, solid mineral deposits resting atop planetary or lunar bedrock.
It functions analogously to terrestrial soil in its physical structure, but it fundamentally lacks organic matter.
Exactly. To test the active tardigrades, researchers required highly accurate models. The origin of the geological data used to create the simulants is derived from NASA's Curiosity rover.
Specifically, the rover sampled the Rocknest deposit.
The Rocknest deposit is located at the Gale crater, positioned south of the Martian equator. The experimental protocol relied on a dichotomy of simulants based on this data.
A comparative analysis of two specific simulants. The first is MGS-1.
MGS-1 is defined as the initial simulant developed to serve as a global representation. It represents the general Martian surface based on aggregated mineralogical data.
The second simulant is OUCM-1.
OUCM-1 was developed subsequently. It is intended to precisely imitate the specific sampling area at the Gale crater. You must emphasize that OUCM-1 places a specific focus on chemical composition, not just the foundational mineral makeup.
It integrates the specific trace elements and salts of that exact location. The experimental protocol required directly mixing active tardigrades with samples of both the MGS-1 and OUCM-1 regolith simulants.
To measure the biological response, researchers utilized longitudinal microscopic observation. This was conducted over a multi-day period to systematically monitor activity levels and morphological changes.
Analyzing the data regarding the OUCM1 simulant reveals specific outcomes. While OUCM1 exhibited inhibitory properties on tardigrade locomotion, the overall impact was significantly less severe compared to the alternative simulant.
The organisms were sluggish, but they maintained basic viability. The results for MGS1, however, document extreme toxicity.
The empirical findings for the MGS1 trials showed significant inhibition and a complete cessation of observable activity.
And this cessation occurred within a strict 2-day exposure window. Total biological immobilization.
Formally comparing the divergent outcomes between the global simulant, MGS1, and the localized simulant, OUCM1, highlights a critical scientific necessity.
It highlights the necessity of understanding specific chemical interactions at the microscopic level. The bulk mineralogy of both simulants is similar, yet the toxicological profiles are vastly different.
This severe MGS1 toxicity prompted hypothesis formulation from the research team. They postulated that a specific isolatable compound within the simulant was responsible for the rapid biological degradation.
To test this, they executed a mitigation protocol. This involved systematically rinsing the MGS1 simulant with water prior to the introduction of a fresh cohort of active tardigrades.
The aqueous extraction phase. The post-intervention observations of this phase are highly definitive.
Following the rinse, the newly introduced tardigrades exhibited almost no reduced activity.
They effectively moved normally and remained healthy.
The chemical deductions drawn from this intervention are precise. The highly damaging elements in MGS1 are demonstrably water-soluble.
Because washing the regolith removed the toxicity, researchers specify that these elements are likely salts, or similar dissolvable inorganic compounds intrinsic to the simulated Martian surface.
This specific chemical lethality forces a comprehensive overview of planetary protection protocols.
Planetary protection is defined as the international, multi-agency regulatory framework designed to prevent bidirectional biological contamination between Earth and extraterrestrial bodies.
Agencies such as NASA adhere strictly to this framework to preserve the integrity of scientific exploration. The extreme toxicity of MGS1 must be analyzed within context as a defense mechanism paradigm.
You can analyze the positive implications of the MGS1 toxicity here. The inherent lethality of the regolith functions as a natural barrier.
It is a chemical defense mechanism against Earth-originating microbial or microanimal contaminants that might be shed by humans or robotic landers. The surface actively neutralizes biological anomalies.
Conversely, you must analyze the negative implications for human spaceflight. This inherent toxicity presents a severe biological hazard to human physiology.
It fundamentally obstructs the adaptation of local regolith for essential survival functions.
Specifically, agricultural cultivation and the establishment of healthy community ecosystems. The water-soluble salts that kill tardigrades will definitively inhibit the growth of terrestrial flora.
This presents a logistical challenge. You might evaluate the viability of the aqueous mitigation strategy in a practical mission scenario.
The laboratory protocol successfully washed the regolith. However, implementing this on Mars encounters the constraint of resource scarcity.
There is a severe scarcity of water in space and on the Martian surface. Consequently, large-scale washing of regolith to neutralize the inorganic salts is currently an intractable logistical challenge.
The volume of water required to sustain even a localized agricultural initiative cannot be systematically diverted for mass soil remediation.
Furthermore, you must transition to the broader scope of astrobiological survival. Regolith composition is only one factor within a highly complex environmental system.
The researchers have detailed specific variables slated for future investigation. These future experimental vectors will isolate the impacts of non-terrestrial atmospheric pressure.
The Martian hypobaric environment must be tested. Additionally, they will investigate the extreme temperature differentials on biological activity.
This reiterates the necessity of a holistic system analysis.
You must meticulously tease apart individual environmental components to accurately assess which variables present drawbacks and which present benefits to the overarching objective of planetary protection.
In concluding this analysis, you must synthesize the inherent paradox discovered in the research. The exact chemical mechanisms that make the Martian surface hostile to human agriculture simultaneously offer the most robust natural defense against the biological contamination of the planet.
The toxic salts ensure the pristine integrity of the planetary environment while actively repelling colonization efforts.
As future missions plan to interact with the Martian surface, you must consider whether the engineering required to neutralize the regolith for human use will inadvertently strip the planet of its primary defense against our own biological footprint.